Yeah. So yesterday we started talking about the insert method for the linked list. Okay, we looked at from three different perspectives. We can insert something in the beginning of the list, we can insert something at the end, and we can insert something in the
In the
middle.
middle. Mhm.
So which one was the cheapest in terms of cost? Again, when I'm talking about cost, you have to give me the cost in terms of time and space. So what do you think? Which one is the cheapest approach?
When we
At the end,
in
doctor,
the beginning.
since the tail is already placed there.
Uh, Again, there was two people talking at the same time.
I believe at the end, since the tail is already placed there.
Okay.
For me, the one in the beginning.
Okay. So the one in the beginning does not require any additional variables. If you like to insert at the end, we looked at two approaches. One approach is to use the loop, okay, scroll from the head of the list, go all the way to the end, and then insert the node at the end. But this is very costly because every time you like to insert something, you have to scroll over the entire list. But if the list is very long, of course, your program will become really slow. So the solution is we create another variable, which we're going to call as tail. And every time you insert something at the end, that particular node becomes the tail. So next time you like to insert something at the end, you can simply use the tail pointer or reference. So this way the cost would be, how long is it going to take? Less time, more time?
The one in the beginning or the one at the end?
No, inserting at the end with the tail variable.
I think it's the same time, but it's like just more space, maybe.
Faster, doctor. Since we don't need to search throughout the whole list, we just need to add something.
Yes. So with the tail variable, if I would like to insert at the end, it's not going to cost me anything. Simply go and insert at the end. Okay. Without the variable, without the tail variable, it will be costly because now you have to scroll through the entire list every time you want to insert something. Okay. So this means using the tail is better with the tail variable. But what if you would like to insert at the beginning? Okay. We also saw this yesterday. If you always decide to insert in the beginning, okay, that is the cheapest because now you don't even have to maintain the tail variable. Simply just go and insert in the beginning. Okay, but what if your application requires the order of the items to be maintained? Yeah, I mean, everything should be sorted in a particular order. So in that case, we have to use the middle scenario where you need to first go and find the previous and the following nodes, okay, and then go and insert the one between the previous and the following. So we saw this yesterday, and I think this is where we stopped yesterday. So this was a very quick review of what we did yesterday. Do you have any questions about this before we move on?
Yes, doctor. I tried to put the code that you did in the video on the website through NetBeans, and there's something I'm not sure of. The head, it's not going to be in the beginning, it's going to be before class, while we update it every time we add a node.
Okay, interesting. Why don't you look at the code in my GitHub repo? Okay, go to the linked objects and copy the code from there and run that. That's the executable code. So the one in the video, it's there to explain these things. But yeah, I understand. Maybe if you copied this directly to NetBeans, perhaps there was some issue there. But the same code is available on the GitHub. Just copy paste from there and it should work.
Okay, so the head, it's okay to not be in the beginning?
Okay, for the linked list data structure, head must always be in the beginning. Head is serving as the hand. It's like the handbrake. Yeah, but for the linked objects example that I explained in the video, the head is moving. Okay, that's okay for that. But for the linked list, the head must be fixed. It must be stationary. It cannot move.
Okay, thank you.
Any other questions?
Yes, doctor. For the tail, when we defined the tail to be the last position, can you go to the tail for the?
Yeah,
Yes.
this one?
Yeah.
Yeah, so tail needs to be defined as part of your class. So here, where did I define the class? Okay, here you would have to define the tail. I think I put this in the red color. So you have to define, so the tail would have to be part of the class if you decide to go with the tail. Okay.
And the main, you mean?
No, not the main. This is your class. This is your single linked list class.
Okay.
All right. And then you're going to use this in the main method. For instance, this is the main method, and you're calling the insert method. So you simply provide the value, and your method
Hello.
takes care of all these things.
عندي محاضرة.
Any other questions?
Yes, doctor. About nodes, what are they again? Because you said it's written node tap equal head in the. What's a node basically again?
Okay, it's better to look at the code then. Okay, so is this visible? Can you see the, or is it too small?
Yeah.
Yeah.
It's just the name of the class?
Yes. So node is just
okay.
a class. Okay. And I'm going to define two attributes for this class. So public integer value and next. Next is of type node. The default constructor is initializing value to 0 and next to null. And the overloaded constructor, which takes these two parameters, is simply initializing the value and the next to v and n. Okay, so that's it.
Yeah.
There is no other methods except the constructors here.
And head is just a name of an object that we would create, basically.
Yeah, so now when I'm defining my data structure, and I'm going to work with the linked list. Here's the linked list. Okay, so this is the linked list class. All right, this is the linked list class. Now here we're going to define, so in my implementation, I'm using head and size. This is conforming to what we studied yesterday. Okay, yesterday we talked about this. So we defined the head and the size. So in the code that I've shared on GitHub, there is no tail. We're not using the tail parameter. Close this one.
Okay.
All right.
And a small question: if we don't have a head or tail, is it not considered a list anymore?
Yes. Yes.
Oh, okay.
At the minimum, you need to have the head. It's also better to have the tail. That will be fine.
Okay. Thank you.
So this is a single linked list constructor. Okay, initializing head to null and size to 0. Okay, this is the method is empty. It simply checks if the size is empty. So very easy to check. If size equal to 0, we return what?
Oh, no.
We return true. Okay, if size is 0, this means the list is empty. If the size is not 0, of course, the list is not empty. Okay. So there's other methods. Let's look at the code first, our understanding first, and then we can go there. Okay. Any other questions? Is this clear to you? How do we insert in the middle? How do we insert in the beginning? How do we insert in the middle?
Just the middle again, real quick.
Sorry?
Just how do we put it in the middle again? Insert in the middle.
Yeah, insert in the middle is, so you have some list. What you need to do is we use two pointers. We use a prev and a follow. So the beginning, it's defined over here in the beginning. Now what we do is we use a loop, and we're going to compare the value of the follow, which will be the first node, compare this with the value that needs to be inserted, x. So if 1 is less than 3, 3 is the one that needs to be inserted. So what we do is we move forward. Okay? If this value is smaller than what needs to be inserted, we move forward. When we move forward, okay, this node becomes prev, and this node becomes next. Oh, sorry, follow. All right? And we keep repeating this thing until you reach the position where this value in the follow becomes larger than this value, the one that needs to be inserted. If this is the case, your loop is going to break, it stops. Now follow is over here. Okay, now we want to find the priv node. Priv node will be the one before it. So what we did was we played a little bit of a trick. Every time you move forward, okay, before you move forward, we update the priv node. All right, and once the loop is finished, you simply go and insert the new node n. So we're going to say n.next equals to follow, and we're going to say priv.next becomes equal to n. Okay, and simply go and increment the size by 1, and that's it.
Okay.
All right, so today we're going to look at two more things. We're going to look at how we search some information, and how we remove. Okay, so let's look at search first. So imagine this is my list. Okay, let's say I'm searching for 3. Somebody says search 3. All right, if you look at your API, remember your API? This was your API. So search method takes a parameter which is of type integer, and it's returning what?
Node.
It's returning a node. So that's what we have to do. Now what we're going to do is we're going to use a temp variable. Okay, and we're going to scroll through the entire list to check if this value is found. So in the beginning, of course, we're going to say node temp equals to head. Okay, and then I'm going to check. I'm going to check while temp dot w or dot x, okay, is not equal to this value. What did we call this? Let's say this is x.
Yeah, okay.
Okay, so while temp dot x, which is this one, is not equal to this x, so what we do is we move forward. Okay, how do we move forward? We say temp equals to
temp.next.
temp.next.
Mhm.
Okay, and that's it. So what's going to happen now is when we start from here, temp.x is 1 and x is 3. Of course, it's not equal. So we say temp equals temp.next. So temp will go to the next one.
But isn't this like the least efficient way to search?
Indeed, there is no other better way to search.
Mm.
Okay, so let's see. Now temp.x is 2. 2, of course, is not equal to 3. So we repeat the same thing. Both temp to the next one. Okay, temp
Sir, won't this take more time?
Of course, very good that you're noticing that this is taking time. Okay, this is one of the problems with this data structure. It's slow. Okay,
Doctor, what if we had duplicates?
very good point. What if there's duplicates? Like, what if there's another node over here that contains 3? It is
It's
possible.
not the index. Oh, okay. It's the value. Sorry.
It
It
is
has
possible.
to be sorted.
It doesn't have to be unique. Okay, this particular one is not even sorted.
Mm.
This means if we start from the beginning and the first time you hit the node that contains this value would be returned. We said that we found it and we're returning this one. Okay, now what's going to happen is while temp is not, so when we come back, of course, this is 3 and this is 3. So we found it. Okay, so simply stop the loop and we're going to return temp.
So it has a lot of flaws.
There you go. So this is my search method. It's returning node, and it's taking integer access parameter. So is this a perfect way of searching something?
No?
No, it's not. Can you think of a better solution?
A better
Searching from the
solution.
middle instead.
Remember, compare this to an array. Remember the array?
Yeah.
Okay. I want you to go and search 3 over here. How are you going to search?
By the position.
Sorry?
Search by the position.
No, but you don't know the position where the 3 is. We don't know.
We start
They're
from the middle.
different.
Don't we do the same thing? We start from here, check, hey, is this 3? No, check this one. 3, no, check this one. 3, no, check this one. 3, yes, we found it. Isn't it kind of similar? It's going to take the same amount of time.
Yeah.
Yeah.
I mean, there are different types of search, so like there's bubble search, I guess, and then like there's, I don't know, but a lot of kinds of searching.
No, you're talking about sorting. Searching, we do have searching. We have something called binary search.
Oh, okay. And then linear search.
Okay, you studied this in CS101. We teach this in CS101.
Yes.
This particular one is linear search. Linear because you start from the beginning and we go and check every one of them. Yes.
And then there's jump search.
What is that?
It's like, I don't know, there's an algorithm.
Of course, there's many other algorithms. Yes, there are.
So what if we use
Can we
two
search
methods?
from both sides?
Very good point.
Like a sandwich?
Can we search from both? Okay, what if the data is already sorted? Let's say this is fine. Let's say. Okay, and imagine there's 2 sides. We can also go this way. All right, so we can see which one is more optimal if I go from left to right or from right to left. Good point. But unfortunately, with single linked list, this is not possible. You cannot go from this way. Okay, that's going to work with the double linked list. We'll study that next week, inshallah. Okay, so is this clear? Everybody's fine with this?
Yeah.
So this is very simple, straightforward. We always start from the head. Okay, and we go right, go all the way until the end. Okay, what if I'm searching for 10? What's going to happen?
It takes a longer time.
So again, we start from the beginning. Temp would be here. Okay, this is not 10, so we go check this one, not 10, check this one, not 10, not 10, not 10. And then we reach at the end.
Yeah.
Okay, we reach the end. So what happens when this becomes null? Would that be a problem?
Yeah.
So let's say temp is
index out of range.
Temp is over here, and we try to compare this. It didn't work, so we say temp equals temp.next. So temp.next is null. Yani, this is going to become null.
We can add an if statement, doctor. If temp next equals null, return null.
So for everybody, is this a problem? Is this a problem to say null.x? Is that a problem?
Yes.
Yeah.
It's going to loop forever with null.
It's going to crash your program.
Yeah.
Okay, so this is not a very safe way of writing code. We have to do something else.
Doctor, if there is a repeated number,
does
he will continue to check? Or?
That's up to you what you want to do. Let's say there's a program that requires you to find all possible 3s, or simply count how many nodes contain a 3. In that case, you'll need to go and check all the way until the end and keep counting. Every time you see a 3, you increment the counter.
Can we check the size of the node or list and say if it reaches above the size, we stop?
That's a very good idea. You're talking about this one, right? So we can
or
do that.
tip.next and then not equal to null.
Very good. We can also do that if temp.next is not equal to null. That's also a good solution. Okay, let's see how this was implemented in our code. I'm going to show you the search method. So here's a search method. You guys can see this, right?
Yes.
Yeah.
Okay, so here's my simple search method. We're defining node temp equals head, and here's our loop. While temp is not equal to null, and we check if there's an if condition within the loop. If temp.value equal to v, this means we found it. If you find it, simply return. So returning over here is just going to kill off this loop, and the method is going to finish. So if it was not what we were looking for, we simply say temp equals temp.next, and we go to the next node. Go back to the loop and repeat. Okay? So
But doctor,
here, if the loop finished, this means we were not able to find the node that we're looking for. If you found it, we would have quit this the loop in the middle. But like this, okay, it will go all the way until the end. Obviously, when we reach over here, this means you did not find something. And here we're suggesting that if the return value is null, this means we were not able to find it. Okay, questions?
Yes, doctor. It says return temp. It will return the head again because temp.val equals to v.
Good point. Look, we're starting from the beginning. Starting from the beginning. Okay. All right. So when we were talking about insert, we looked at 3 cases. We wanted to insert in the beginning, and middle, and end. Okay, so we're going to have something similar. So let's create an imaginary list. Okay, so let's see how do we remove something from the beginning. Okay, so here's a beginning case. Let's say I want to remove 1. This means first we have to go and search 1. All right.
So create a temp, I don't need.
So we start from the beginning and we check, hey, is this the node, the node that we're trying to remove, does that happen to be the head? So if this is the case, okay, if this is the case, then what we need to do is we need to readjust this. All right. So how do we do that? First, you need to go and search the node. Okay. So let's see. How do we do that? We're going to define node temp equals to head. Okay. So we have temp over here.
Okay.
Doctor, don't we have to use the search method, but instead of returning the value, we remove it?
That's a good point. I mean, since you're trying to remove, and remove will involve searching the value first, we can indeed use a search method that we just wrote. We can do that. However, I mean, just for the sake of understanding, so let's do that. So while, okay, let's say we're trying to remove x, okay? So again, like what we did before, while temp is not equal to null, and we have to check if temp dot x is equal to x. This is the node that needs to be removed. So in that case, I'm going to stop the loop. Okay. Otherwise, we simply just go to the next one. So temp equals temp dot next. Okay. Again, this is not complete code. It's just a piece of code that we're using to search the node that would be our tag for removal. So let's say if I execute this code, so temp is in the beginning, and let's say x is 1. So this will become true, and we break the loop. Now, once we break the loop, this means we have found the value that needs to be removed. So we can check, hey, is this the first one? Does it have to be the first one? So how do I do that? If temp is equal to head. Okay, so it's the same memory location, which is pointed to by the head also, which means what we're looking for is in the beginning. So if it is in the beginning, all what we have to do is, okay, if this is the case, what we need to do is we need to say this. Okay, we'll simply say head equals to
Temp.next or head.next.
Head.next. Okay, why? Because now we're changing the position of the head. So head goes over here. So this is gone basically. We have updated the value of the head. Head was previously pointing to this node. Now after we execute this line, it's not pointing to the same node anymore.
Okay, else?
Effectively, now we've lost this particular node. We cannot access this node anymore. We've lost the anchor for it. Remember yesterday I told you never to move the head unless it's absolutely necessary, unless you know what you're doing. So this is one of that situations. When if you move the head, you're going to lose this node. You cannot reach this anymore. Okay? But this is intentional because we're trying to remove it. Now, here's the question. Did this node actually get removed from the memory or is it still there? Okay, we cannot access it anymore.
I think it goes to like trash or garbage thing, and then like it gets removed by the compiler or something.
Okay, very good point. Yes. So the computer's operating system platform is responsible for something called garbage collection. All the memory which is not accessible anymore goes back to the operating system and it's going to reuse it for some other purpose. Unfortunately, for Java virtual machines, okay, for Java programming language, it works on a virtual environment. It's called Java Virtual Machine. It's not directly controlled by the underlying operating system. So what happens is all this memory which is used, okay, it just stays there hanging until the program quits. Okay, once the program quits, all the memory will go back. So this is a bit inefficient when it goes to Java, but for programmers, you don't have to worry about it because once there's not enough memory available, JVM will go and collect all of this garbage. So that's okay. All right, so this is what we did. We simply moved the head to the node next to the one that needs to be removed. And now this node is not accessible anymore. And we're hoping that the JVM and the operating system will just go and take this away.
Okay, now it's like if it's not the head.
Like C++, okay, you have to remove it. If you don't remove it, it will be still there. It will become a vulnerability for the system, for the hackers to exploit. And this is one of the reasons, okay, systems get hacked because you left some dangling reference or hanging memory location somewhere which is accessible to a hacker. Okay, so that's pretty much it. That's all we had to do. Just simply go and move it like this. All right. Now let's look at the case where we would like to go and remove something from the middle. Okay, let me do this with a different color. So let's say we want to get rid of 3. Okay, do you think the same code is going to work? This code that we wrote a few minutes ago?
No.
Yeah, we were using this thing for search. So let's start from the beginning. Let's say I'm trying to remove 3. So we start from here. This is 10. Of course, it's not 3, so we'll say temp equals temp.next. So temp goes over here.
Yeah, until it goes to 3 and then.
So and then it goes over here.
Okay,
and we found it. We stop here, and then we go and check. Of course, this is not the beginning case because now temp is not the head. So it's something
else.
Okay. Can we check this is the end or not?
Yeah, we can do that by like doing size, like checking by the size.
Okay.
Not the size. We can check if the dot next is null or not, I think.
Very good. We can say if temp dot next is equal to null, this means this is the last node. There's nothing after it. Let's say it was 4. And dot next is null. This means there's nothing after it. So we simply go and remove it. But now there's a little problem here. The problem is my temp is already sitting here on 4. Okay, I cannot go back I cannot go back. Effectively, I should be doing this. I should be able to say 3.next equals to null. Okay? But if temp is already moved over here, then you cannot go back. So, can you think of a solution?
Can't use the
Temp dot
types.
next equals 2.
Come on, we talked about it yesterday.
To go backwards, or
No, we cannot go backwards, but you need to
what's the
remember
question again?
the one before it.
We want to reach 2 after we've reached 4.
No, look. So if you're looking at this code, the temp is moving. This is temp. Then it goes over here. This becomes temp. Then it goes over here. This becomes temp. Okay. Let's say I was trying to remove 4. So once I reach over here, I realized, okay, this is the node that is at the end.
Can't we do size -1?
No, can we use the previous and follow?
Very good. We have to use previous. Okay. So that's what I'm going to do. I'm going to change this just a little bit. I'm going to define previous. Okay. And here, every time you want to go to the next one, before you go to the next one, here, I'm simply going to write another code. I'm going to say previous equals to temp. Okay. So just added 2 lines of code over here. That's going to solve this problem. Okay, let's look at it. Well, how is this going to impact? So we start from here. This is temp. Okay. In the beginning, where's previous? Did we define it?
Yeah.
Yeah, we defined it, but we didn't give it a value.
Yeah, we defined it, but we did not assign it anywhere. So it's just hanging somewhere. But let's say we come over here. If temp, okay, this is not true. So we get over here. We say previous equals temp. So this becomes previous. Okay, that's my first node. And then we say temp equals temp.next. So temp moves over here. Okay, so once the loop finishes, when we get back over here, notice where's temp? On 2. And previous where? Come on.
One before.
Yeah, remember yesterday we studied previous and following?
Yes.
Yes, whenever we reach something, we can make the prev the one before it.
Yes. So
Which
let's see what
should-
happens now. Let's say I'm trying to remove 4. Okay. So let's see what's going to happen. So temp is here now and prev is over here. So while temp is not equal to that, so we go and check, hey, is this 4? No, this is not 4. So we say prev equals temp. Okay. So prev becomes temp. This becomes prev now. And we say temp equals temp.next. So temp goes where? This one. So far, so good. Again,
Yes.
go back, check the loop. Okay, is this 4? No, it's not. So we're going to say previous equals temp. So again, previous equals this one. Okay, and then we say temp equals temp.next. So temp moves over here. Now again, we go back to the loop and we see if temp dot, okay, we found it. Okay, let's say I was looking for 4. So we found it, we stopped. Now notice temp is on 4 and prev is on 3. Okay, so now this is going to work. We're going to say if temp.next equal null, this means this was the node that we're trying to remove, and this node happens to be the last one in the list. All I have to do now is I have to say prev.next equals to null. Okay, so this is prev now. Prev.next equals to null. Yeah, I mean, this is gone. This connection is gone. We cannot reach this anymore. Can you reach 4 or is it gone?
Gone.
I think you can reach it by 10% by 4.
Yes, good. So we cannot reach it, but it's still there in the memory. And Java is going to take care of it. The JVM will take care of it. So you don't have to worry about it. Okay, is this clear?
Yes.
Okay, let's say we were trying to remove 3, something in the middle. How is this going to work? Do you think this is going to work the same way?
You can just say if it reaches the value we need, just break. If
We just have to change the arrow just like in the beginning. So the priv will not point to the one you want, but it will point to the one after it.
Okay, so there you go. Now, so again, starting from the, let's say I'm trying to remove 3. So in the beginning, temp is going to be here, then temp moves here. Okay, this is priv. And then we go to the next one. So this becomes temp and this becomes priv. Okay, so we found the one that we wanted to remove. This is 3. That's what we want to remove. Okay.
So
how do we know that this is in the middle? Can I know that this is middle?
Yes, if temp
Like
dot
if the
next
next
is not equal to
null.
none.
So if temp dot next is not equal to null, this means it's in the middle. Okay, it's in the middle. And this was over here, this was telling us that this is the last one, this is at the end. Like here, if temp.next is not equal to null, this means we're in the middle. Like if you're in the middle, what we have to do is simply priv.next equals to temp.next. That's what we're going to do. Okay, we're going to say priv.next equals to temp.next. Okay, so this is priv. Priv.next equals to temp.next. And this connection is gone. Is this connection still there?
Yes.
Good question. Yeah.
It is still there. But can you access this node? Can you reach there?
it's null.
Until you, unless you have like a different form, like doubly linked list or something.
No, let's only keep focus or keep our focus on this one.
No, still now you can't.
Yeah, you cannot. So you cannot access 3 anymore. That's it. It's gone. But 3.next is still pointing to 4. So we don't care about that because this is not reachable from here. So effectively now your list contains 3 nodes: 1, 2, and 4. Okay? Does it make sense now? Is this clear?
Yes.
So if you want to remove something from the list, there's 3 situations or 3 scenarios. Either the node that you're trying to remove is in the beginning. If it is in the beginning, we move the head. If it is at the end, okay, we have to, so for both of them, for middle and the end, we have to use a priv. So if you use a priv, you can easily detect if the node that you're trying to remove is in the middle or at the end. If it is at the end, simply say priv.next equals null. If it is in the middle, we say priv.next equals temp.next. Okay, any question about this? Everything fine?
Can nodes be null and still exist? Like,
no. I think what you're asking me is already covered in the video. So if I define a variable like this and make it point to a node, and then I say n equals to null, okay? What's happening is this connection is going away. It's not there anymore. It's not referring to the memory location. It's just a reference with no memory attached to it. So think of it like just a key which does not open any car.
And does the node, like 1, 2, 3, 4, does it have a set size? So we can just say node.size to check how many nodes there are? Or do we have to make a loop?
Of course, you have to. I mean, this is what we're going to do. Just a second. We're going to look at the code. So every time you insert something, you can increment the size variable. Every time you remove something, you have to decrease the size. Thank you for pointing this out. So for each of these cases, we have to say size minus minus. And remember, in our API, we were saying this. This is our API. We're saying the size variable. See that?
Oh, yeah. So it's not like the normal array list or arrays where you just say if it's less than the array dot size and then continue, or length. you can continue the.
We can still use that. We can say this. We can say the singular linked list dot object. Okay, singular linked list object dot size. We can do that. If you make this public, of course it's accessible.
Oh, okay.
I believe the code that I've written is doing the exact same thing. Let's look at the code now. So this is the insert method. We already talked about it. This is the remove method. Okay, so let's see. Now there's some other scenarios. These are what we call as the boundary cases. What if the list is already empty? So instead of going and looking at the rest of the code, why can we not simply put a condition if head equal null means the list is empty? I don't need to go over the rest of the code, just stop here. Okay, so this is what we call as boundary cases, and we try to handle these situations to optimize or to make your program faster. Okay, so if head is not null, this means there are some nodes in the list. Naturally, the list is not empty. So we go and look at the two cases. So first one is, what if what we're looking for is the head? So if that is the case, we simply say head equals head.next. All right, which case was this? A minute ago we saw this. Oops. So if what we're looking for is already there in the head, this means we need to change the head. So head equals head.next. That takes care of it. So this is your situation when the node that you're looking for is a head. Okay. Now, in this particular code, look, I'm defining node previous and node temp. So in the beginning, node previous is head, node temp. And we use a loop and we check. Every time we look for a value in the node, we move forward. Simply say previous equals temp, temp equals temp.next. So this is exactly what is happening over here with the blue line. So node priv, and after the conditions, I'm saying priv equals temp and temp equals temp.next. So this is what is happening over here, exact same code. Okay, what if you found the node that contains the values? In this case, okay, we put this condition previous.next equals temp.next. Now this is genius. Look at this. What I've done is I've merged both of these together. Now pay attention carefully. If the node that needed to be removed was the last one, this was 4. So we're saying previous.next equals to null. Remember this?
Yes.
Yeah.
Yeah, we said this thing a few minutes ago. And if it is in the middle, okay, we were saying previous.next equals temp.next. Clear? Now, how do I merge these two together so that they become the same code? All right, pay attention. Let's say this is temp. So temp.next is null. Here, I'm going to go with the green color code. Here, instead of
then
null,
add an or.
if I say temp.next, would that work? Look at this. This is temp now. Okay. And this would be priv. Can I say priv.next equals temp.next? Can I say that? Remember, what's the value of temp.next?
Temp.next is actually null, so.
Very good point. So temp.next is already null. If I say that priv.next equals temp.next, and I know for sure that temp.next is null, fine, this would become null, which means I can reuse the same code. See, there's no difference between this code and this code.
Oh, okay.
So to play it cleverly, what we can do is we can merge it together. We can simply say that, okay? Regardless if it is in the middle or if it is at the end, the same line of code is going to work for both of the situations. All right. So, and one other case that we did not consider. What if what we're looking for is not there? Let's say I was trying to remove 5. You see 5 in the list?
No.
So what's going to
To
happen?
return null, we have to.
We keep going all the way until the end, and temp becomes null. And when temp becomes null, we cannot do anything. We cannot go and remove any of these.
Yeah, we
So
have
if
to set the
that's the
case
case,
word.
yeah, so if that is the case, okay, we're trying to look for the node and there's no node there, so we simply say return false. Okay, by default, we return false. This means that we were not able to remove it. Yeah, we did not find it.
Mm.
Clear? Any questions about this?
Why can't we return null instead of false?
Okay, so the way we've written this method, remove is returning Boolean. Okay, so what we're saying is, if you were successful, we will return true. If the node was not found, okay, we will return false.
Okay.
Okay, so if you were able to return, find the node, like in this case, we return true. We found the node, we return true, after removing it, of course. If we were not
Yeah.
able to find it, we're going to return false.
Okay.
Okay, so that's pretty much it. This is your remove method. This is your insert method. You already saw that. Search method, is empty method. Okay, now question. What if somebody wants to check the size of the list? How can we do that? How can you know how many nodes are there?
We make an integer called size.
Okay, look at my
and
input.
then
I am defining a size variable. I'm simply saying integer size. It's very simple. Okay, every time you insert something, we're going to increment the size.
Increment, yeah.
Every time you remove something from the list, we're going to decrement the size. But question, what if we did not maintain this? How can I find the size of the list?
By doing a for loop or like whatever loop and then
Okay, good point.
putting a counter.
Yeah, so for example, let's look at the size. Imagine the size is not there. And you have some list that contains some number of nodes. We really don't know how many nodes are there. Okay, we don't know. Like, how do we figure out how many nodes are there? Can I write code for this?
Yeah. We
Okay,
can,
same thing as
the
before.
object's name dot size.
We're going to say node temp equals to head. Okay, so while temp is not equal to null, we simply say size plus plus, and temp equals temp dot next.
And then return size.
Okay, and of course return size. Very simple. So start from here, check, is this now no, increment the size, go next. Is this now no, increment the size, go next. So you keep going on all the way until the end. Whenever this becomes null, we stop the loop and you have your size. But is this very efficient or not?
No.
No.
It just takes time.
It will take time anyways.
The variable method is easier because whenever you add, it's already like you already have a number.
Good. Variable is more efficient because every time you insert a remove, we're simply updating that. And if somebody wants to know the size, they'll simply say, hey, just give me the dot size value, and you have the size. But this one is not efficient. What if the size of the list is like 1 billion elements? And every time somebody says, give me the size, you have to go over the loop and check every single node in there and then return the counter's value. Wouldn't that be costly?
Yeah.
Okay. So we come to the end of the linked list data structure. Okay, this is a single linked list implementation. Now, if you want to try, okay, I have created a tester program. Okay, I would like you to go and try this. Download this in your machine, open in NetBeans, and then you can go and work with this. So we're defining a single linked list L object. We create a new linked list object. and we say L dot insert 10. Actually, it's going to go and insert 10. L dot insert 20. Okay, and then we simply we say L dot remove 50. Like, is this going to work or not? Remember, the remove method is returning Boolean.
Yeah, so it will return false.
So they should print false because this is returning false, it will print false.
Mm-hmm.
And then we say print L. There was a toString method, I did not talk about it. Okay, it's simply going to print everything inside the list. And then we say L dot search 30. Remember the search method?
Yeah, to return null.
It will return null, okay, because the search method is returning a node. So we'll try to go and find a node that contains 30. We don't have a node that contains 30, so it's going to return null. And then we say L dot insert 30, L dot insert 40, then we print, and then we remove we remove 10, and then we remove 40. So at the end, what's there left in the list?
20 and what? 40? No, we removed 40 or not? 20 and 30.
Yes. So what's left in the list is 20 and 30. Okay. So go ahead and play with it. Add and remove elements. Search for elements. Yeah, that should give you some practice.
Okay.
Okay. So let me show you where we are now. We have just finished with the singular linked list. On my website, there's a singular linked list animation. If you click on it, okay, it's a nice animation on an external website called Visual Algo. Okay, it's a play on the name Visual Algorithm, visualalgo.net/list. So go ahead, play with it, insert some values in there, and see how this works. Okay, this is a nice animation there. All right.
Okay.
At the end of every week, we typically do a tutorial. So here's a tutorial. Okay, so we have some questions over here. What we do is try to write code for each one of them. Now, I've already provided the solutions for each one of them. So this is the solution for tutorial 2, solution for tutorial 3, and so on.
Okay.
So you can go ahead and look at it in your own time. So here, very quickly, write code to duplicate an array of type strings. Like, this is revision for CS101 and 102. Okay, so I'm sure you can do this thing very easily. Okay, here's another question. Create a class node with these attributes. So defining integer ID, string name, double GPA, and node next. Write a tester program to add 3 students. Provide your own details. So this is very similar to exercise given in the video that I asked you to watch. Okay, go ahead and try this in your own time. Question number 3 is give an algorithm to find the node before the last. Find the node before the last in the singular linked list. So did we do that?
Yeah, the search method.
See, it will be exactly this code. So you need to define a priv. Okay, go all the way until the end. Once you reach the end, okay, temp would be on the last node, and priv would be where?
The one before it.
Yeah, the one before it. So we return the priv. So you already know what the code is. Okay. Question number 4, write Java code to add a node in the beginning of a list. But can we do this?
Near the beginning of the list. Yes.
We already did that yesterday.
Yesterday.
We did this thing yesterday, how to insert a node in the
Beginning means at the head or after the head?
Yeah, at the head, before the head.
Oh.
So this is that code. Okay. Question number 5 is write a add middle method in the singular linked list that traverses to the middle of the list and inserts the node n. Okay, this is interesting, how to do this one. Okay, I want you to give me an idea. You'd like to insert this in the middle, exact middle. Remember, we studied this yesterday. How do we insert something in the middle? But this is not exact middle, it's somewhere in the middle. And the
Yeah.
question of the tutorial is saying you have to add it exactly in the middle.
I mean, if we have a size variable or whatever, we can just divide it by 2 and then find the middle.
Very good, excellent. So yeah, we're assuming that we already have the size variable. We're going to go to the exact middle of the loop, exact middle of the list, and we can simply go and insert this node in the middle, just like what we did before. Can you guys do it, or should I do it for you?
I think it's clear, Doctor. We did some.
So you can do this thing on your own?
Yeah.
I believe.
Okay, good. Right, number 6. Write a find ID method that traverses the list for a node containing ID of a student. It returns the node, a reference to the node. Isn't this exactly what the search method does?
Yeah.
This returns a reference, not the value.
Yeah, so when you return node, that is a reference, a pointer to the node. Okay, this is the exact same code. The only difference is here, instead of integer x, you're going to return integer ID.
Yeah, I guess the same then.
Okay, so the exact same code as search method.
Yeah.
Let's look at the last question. It says try to bring the first method that traverses the list for a node containing ID of a student. It detaches this node from the list and attaches it to the head of the list. Okay? Think about it. What do we have to do here? So you have a list. It's asking you to find the node at the end. Is it at the end, or in the middle, or in the beginning, or what?
It detaches the node from the list and changes the head. I mean, it doesn't specify, so.
It removes the ID of the student that they want and puts it in the beginning.
Yeah, so first you have to go and search the student wherever it's located in the list. You have to detach it,
And then we
remove the node, and then insert this in the beginning.
So we use the temp dot, and then like, I don't know, point the pointer to the head.
Okay, let's do this thing. This is considered as a little tricky, but let me give you an idea on how to do this one.
What does traverse mean, Mr. Doctor?
Yeah, so let's do it without using the single link test, just to understand how this is going to work. So let's say these are some nodes, and these nodes contain the IDs of students. Okay, naturally the IDs of students are integers. Okay, so this is some list. Right. So we have to first search. Okay, then we have to detach, and then we have to attach. Okay, that's what it says. First, you have to search for the node that contains ID, detach this node, okay, and then attach it in the beginning.
So search, you already have the method.
So search we already have, okay. Let's say, but we don't know where the node is. That's very important when we're doing the detachment. If the node is somewhere in the beginning, or if it is somewhere in the end, or somewhere in the middle, we don't know. Okay, so what should we do?
Put all 3 cases.
So this is easy. If it is the first one, you don't really have to detach it, right?
Mm-hmm.
You agree with me?
Yes, so we check.
If it is the first node, okay, what's the point of removing it and then adding it in the beginning? It's already there in the beginning.
Yeah, so we put, if it's equal to head, then don't do anything, basically.
Exactly. So if the node that you're looking for, if the student ID is happens to be the head, we don't do anything. That's it. Just quit. If it is not the first one, okay, and then what we have to do is we have to search. All right, so this is the situation when we're trying to remove from the middle or at the end. And we're trying to be clever about it by using the priv. So we can do the same thing here. We can say priv, and we can have the next sort of following, or the 10. Okay, so let's say it was this one. This is the one that needs to be removed. So in this case, what we do,
So the prev has to point on the one next to temp.next, and then the temp, I think it will like point in the beginning or something.
yeah, so if it is in the middle, okay, we can figure it out. So we can say that priv dot next would be equal to
Temp.next.
temp dot next. Okay, so this is what is going to happen.
Mm-hmm.
Okay, what else?
Temp.next is equal.
This is detached, successfully detached. But now
Yeah.
let's detach it, bring this to the beginning.
So now temp.next is equal to head or something.
Very good. So temp dot next equals to. Did you take this course before?
No.
Okay, I don't know. I mean, it feels like you already know everything that I'm mentioning.
I just
So
finished CS210.
Doctor, is it temp.next or just temp equal to head?
No, if you say temp equals head, the temp goes here. No, that's not what we want. Okay, we have to say temp.next equals this. So this one is going to be disconnected. And now we're saying go back.
Yes.
Okay, but now we forgot one thing. Here, where's your head?
Yeah, now the head needs to
Head needs to change.
Yeah.
So head equals to
head.next, yes.
No, head equals to temp.
Oh yeah, okay.
Okay, remember this is gone.
Mm-hmm.
So now you're saying head equals to temp. Now this becomes a little funny. Okay, so we're starting from here. Now this is your first node. This is your second node, third node, fourth, sixth, and so on.
Mm-hmm.
Does it make sense to you?
Yes.
Yes.
Okay. I don't know. I hear only 2 people out of 17 talking. All right. What if the node that we wanted to remove was, I don't know, let's say this one?
It's probably the same thing, just like the priv will.
Same thing. This would be temp, and this would be priv. Okay. Now what do we do? We have to do
Now the priv
equal.
next will be null, and the rest is the same.
So you're going to say priv dot next equals to null. Okay, so this becomes null.
And then the same stuff. Temp.next equals to head, and then head.
Can I not reuse the same code? Instead of saying this, can I not say temp.next?
Yeah, same code.
You can, but the result will be null.
Yeah. And then how about temp.next
equals to head, and then
equals to head? Yeah, so this is temp, so temp.next will become, I don't know, I don't have room to write this, but it will go to this one. And then head equals to temp.
So the same code, basically, yeah.
So exactly the same code. Very good. All right, so is it too hard?
No.
No, it's kind of simple. Doctor, I have a question.
Yes.
For the best way is not to write null, but temp.next, since we may add a node sometime while we're coding, or while the user is coding, the user is using the program.
Okay, so you're talking about this particular problem, or in general?
Yeah. What I'm asking is that if we write priv.next is equal to null, it may cause a problem. What is it?
No, it's not really a problem. But if you do that, you have to write 2 if conditions. 1 if condition for the middle case, 1 if condition for the last one. But if you just go with temp.next equals temp.next, you don't have to worry about the middle or the last.
Right.
It works with both.
Doctor,
Yeah.
can't we do from the before we add any nodes, increment the size, the integer size, just so we can have the size of the node, so we know when to stop. Do you understand what I mean?
I did not really follow your question. Can you go again?
So we have int size, and then before we make a new node, we increment the size, and then we continue. And then whenever we want to check the middle or last one, we just use the size. It's already pre-defined, instead of making a for loop for the size.
Your question is not very clear, but what I'm trying to, I think what I understood is that what you're saying is every time you create a new node, somehow we remember the index position. So this way we don't have to jump to that particular node. Is this what you're saying?
Just the size in general. Instead of making a for loop,
yeah,
we can make just define the size from the start, so that instead of saying, oh, if it equals null, stop, we can just say if it's greater than or equal to the size.
Remember the reason that we're doing linked lists is because of arrays. Array is a better solution when it comes to searching and finding information. But arrays had two problems. Number one was fixed size. Once you define the size, you cannot change it. So if you do the same thing with linked lists, if you fix the size, then what's the point? Okay, so size has to move. It has to be dynamic. So that's like the strength of the linked list, that it can take any number of data, almost unlimited size, depending on the hardware. As long as you have enough memory available, you can use all the memory for the linked list.
Yeah, but we can always decrement as well. Like if we remove a node, we just add decrement the size. It's just a reference, something we can have as a backup, instead of making a for loop for the size, as we talked about before.
Yeah, that's the thing. I mean, in any implementation, any linked list implementation, okay, it's better to have the size variable instead of using a size method to go and check the size. So yeah, you will find this thing. In any implementation, you have to define the size. It makes your life easier.
Yeah.
Okay, so we're done with the first tutorial. Now, tomorrow there won't be any class. Okay, next week, inshallah, when I see you on Sunday, we're going to start with double linked list. Okay, Sunday we're going to study double linked list. Monday, inshallah, we're going to look at the circular linked list. We're going to work on tutorial number 3. And Tuesday, we're going to start with the next topic, okay, which will be in week number 4, which is foundations of mathematics algorithms. And next Wednesday, okay, is going to be your first assessment, first major exam. So the major exam is going to cover whatever we've done this week and whatever we would have done next week. Okay. So any questions for today? We're done for today.
Doctor, I have a question from yesterday.
Yeah.
You talked about embedded classes. Can you explain them, or like just give us a brief, please?
Oh, it's just a way of writing code. Some people prefer embedded classes. So if you look at this particular project and go here. So if you look at this one, these are 3 different classes. 3 classes in the same package or same folder.
Okay.
Now, what I can do is I can put these 2 together in the tester. Instead of having 3 different files, you can have just one file. So it will be a class inside another class. This is embedded class.
So you're gonna have node and like single linked list in one class, and then the tester in another class.
So you can put all 3 of them in one class. I thought you guys studied this in CS102.
No, he didn't mention it actually.
Okay.
Well, we did study it, but
it's a practice. I mean, it's your preference. If you want to go this way, that's fine. But we prefer this. I mean, every individual class in a different file. That's better. That's yeah.